Look at this graphic. It shows the cloud, a concept we are all familiar with. It promises that you can store your documents and access them seamlessly, anywhere, anytime, on any device. But for systems engineers, the cloud doesn't exist. It is a consumer abstraction. What you are actually interacting with is a strictly organized assembly of physical hardware and logical routing protocols. Every modern network, whether it is a small home setup or a massive global enterprise, is built on a strict division of labor between three elements: end devices, intermediary devices, and network media. We are going to construct a modern enterprise network from first principles. We will start with a single room and scale our way up to a global infrastructure. Grasping this physical and logical architecture is the absolute baseline requirement for modern systems engineering and troubleshooting. You have to know how the machine is built before you can fix it. This diagram outlines end devices. A message originates here, flows through the network, and arrives at another end device. This category includes desktops, laptops, mobile phones, IP phones, and network printers. Here we see the division of labor at the endpoint level. All these devices carry an IP address to communicate, but take on specific roles. Clients run software to request resources, while servers provide those services, like hosting web pages or storing corporate files. If you connect a few computers together without a dedicated server, you create a peer-to-peer or P2P network. In this setup, every device functions as both a client and a server simultaneously. This design has its uses. It is inexpensive, highly accessible to set up, and requires no dedicated server hardware. It works well for simple tasks like sharing a printer in a small office. This chart highlights the engineering limits of a peer-to-peer network. Look at the disadvantages column. There is no centralized administration, and security is weak. Because every device acts as both client and server, processing load increases with every new machine. The network cannot scale. To build a true enterprise network capable of handling hundreds or thousands of users securely, we must abandon the peer-to-peer model and introduce dedicated infrastructure. Let's begin the physical build. We have a blank slate with two isolated end devices that need to communicate. We introduce our first intermediary device, the switch. Instead of wiring computers directly together, both connect to the switch, which actively directs data between them. The functional boundary of a switch is strictly geographic. It is engineered to connect multiple end devices sitting within the exact same local physical space. By connecting these devices through a switch, we have just created a LAN, a local area network. A LAN spans a small geographic area, like a home, a single office, or a campus. It is defined administratively as a high-bandwidth network managed entirely by a single organization or individual. Switches and the local area networks they govern form the fundamental high-speed building blocks of all corporate network infrastructure. Before scaling this design up, we must address the physical layer. How does the signal actually travel from the PC to the switch? Communication across any network is carried through a medium. Network media is the physical carrier that allows a message to travel from its source to its destination. The common standard for internal LANs is copper cabling, like Ethernet. It carries data by encoding it into rapid electrical impulses sent down the wire. For vastly higher bandwidth over much longer distances, engineers use fiber-optic cabling. Instead of electricity, fiber encodes data as pulses of light traveling through glass. And for mobile endpoints, we use wireless media. This eliminates the physical tether entirely, encoding data through patterns of electromagnetic waves. An engineer's choice of media dictates the absolute physical speed, distance, and reliability limits of the entire network design. Our single LAN needs to securely communicate with a completely separate LAN in a different city. A switch cannot cross this boundary. It is engineered for local traffic. We need our next intermediary device, the router. Routers connect independent networks and direct traffic between them. By routing traffic over these vast geographic distances across cities or countries, we establish a wide area network, or WAN. Unlike a LAN, WAN boundaries are typically administered by external service providers, not an organization's internal IT department. Home users typically connect to these providers using asymmetrical cable or DSL, where download speeds are prioritized over uploads. Businesses require dedicated leased lines or Metro Ethernet to guarantee symmetrical speeds and manage services.
While switches rule the local office, routers navigate the globe. String enough of these LANs and WANs together, and you have the internet. Physically wiring the infrastructure is only half the job. A network must be meticulously mapped out to be managed and secured. Engineers use two distinct mapping paradigms. The first is the physical topology diagram. A physical map tracks the exact geographic location of devices. It shows where cables are installed and identifies specific physical ports on every switch. The second is the logical topology diagram. A logical map abstracts the hardware away. It tracks device IP addresses, subnets, and the virtual pathways data actually takes as it flows through the network. Both maps are mandatory for survival in IT. You use the logical map to figure out why data isn't flowing correctly, and you use the physical map to find exactly where the broken wire or router is located in the building. 30 years ago, corporate infrastructure was heavily fragmented. Buildings were cabled separately for computer data, telephone voice traffic, and video feeds. Each network used its own rules and proprietary technology. Maintaining 3 parallel sets of media and intermediary devices was deeply expensive and inefficient. Today, we use a single standard, the Converged network. IP phones, streaming video, and standard data all ride the exact same physical media. They are routed by the exact same intermediary devices, operating under one set of rules. We have taken a simple data exchange between two computers and scaled it up through copper media and local switches, bridging the gap with routers to create a global converged WAN. By mastering this architectural triad, end devices, intermediary devices, and media, you possess the structural bedrock required to configure, defend, and troubleshoot any modern IT infrastructure.